Linux and Unix operating systems are the backbone of countless organizations worldwide. From critical business servers to web infrastructure, Linux plays a foundational role in securing information and enabling operations. As security professionals, we must understand not only how Linux manages user authentication, but also how password hashes are stored and accessed and interpreted. Now, this knowledge allows us to identify weaknesses, verify defensive controls, and, when authorized, prepare for ethical password analysis. And in this lecture, we will focus specifically on collecting Linux password hashes. We are not yet attempting to crack or brute force them. That will come in this next lecture. But instead, in this lecture, we are going to explore the files responsible for password storage, examine the format of password entries, learn about salts, hashing algorithms and why they matter, and practice extracting hashes using standard Linux commands. Now understand each field in this critical system files and their impact on authentication and security. And by the end of this lecture, you will not only know where the Linux password hashes are located, but also how to properly collect and interpret them for use in later analysis. So what we will do now is firstly change the Linux user password, because my password is, since this is a virtual machine, I have set the password to 123 for the easy access. Let's set it to something hard. This is our password that in next lecture we will try to brute force it. Let's change the password, and here we are, password 1980. Perfect. Also enable the, or let's disable it. But before explaining the hash collection, let me acknowledge an important principle here. If you have a physical access to a Linux machine, you can usually reset passwords without cracking them. Now, this is possible through a single user or rescue mode. Now you can, there's a steps in order to do that. First, you just need to reboot into the bootloader. Actually, yeah, we have it here. I will explain it one by one how you can do it on your own. First, you need to reboot the machine and press escape keyboard to open the bootloader. Select the top menu option and press E to edit. The third step is locate the line beginning with systemd unit rescue target. This is the Linux that specifies the kernel path, and at the end add this one here, right? And this tells systemd to boot into a rescue mode. And after that, press F10 to boot, and the system will stop and ask, press enter for maintenance, and after pressing enter you are dropped into root shell. And from here, reset password using passw root command and passw your username you want to reset. Now this changes the administrator password, and this changes the specified user password. And finally, type exit to return to a normal multi-user mode. Now, this is a very good way to reset it. Now this method bypasses the need to crack the hashes entirely, and it demonstrates that physical access equals control, reinforcing why servers must be physically secured. However, this method does not recover the original password. You are simply overwriting it. And the same method also uh, you can do the same method in Windows as well, but just the different steps, right? You can change the passwords of Windows machine if you forget it, basically with the same principle. Now let's collect our passwords. Our objective is to perform ethical password auditing. Now we need the actual password hashes. Now these are stored in the etc shadow file. Let's open the terminal here. Cat etc shadow. Run it, and you can see if executed as a normal user, the system will respond that permission denied. Now this happens because only the root user has permission to view this file. Now regular users cannot access it for obviously security reasons. What we need to do is we need to start it with the elevated privileges. Sudo cat etc shadow. Okay, we need to enter our new password 1980, and here we are. Now this is our output. Let's understand the output here. The first, we have the username. In this case, for example, we have roots, other tools, and we have a Typhoonix, which is me, right? In this session, this user account. And after that, we have a password hash. This is the hash we are looking for. Now, if you see this ternary operator or this asterisk, this means the account cannot log in with a password. But in this case, we are seeing in the Typhoonix, we are seeing the hash, right? Here. And after that, we are seeing the last password change. Now, this is basically the number of days since January 1, 1970. Now, this is the Unix epoch. The minimum password age, minimum days before the password can be changed. We have changed just now. The maximum days before the password must be changed. This 99999 means essentially never. And we have a warning period, days before expiration when users receive warning. And here we have two more fields, inactivity period and account expiration date. Basically there is none. Basically the inactivity period here, they put it here. Inactivity period means days after the expiration before account is disabled, and the last here, account expiration date, the absolute date when the account expires. And we also have a system accounts. You can see we have a bunch of system accounts. Entries like daemon, bin, sys, or systemd timesync, systemd network. We also have a dbus here, basically color D. Now these are service accounts. Their password fields often contain this asterisk or this ternary operator, meaning the login is disabled. And we also have a user account, for example Typhoonix, right? Now in Typhoonix we are seeing the hash. This is CHA512 salted hash, This is the salt and hash follow with account policy fields after. Now let's copy this hash and understand this salted hash more detailed. New file. No, actually, we new text file. Okay. Basically, this ID specifies the algorithm. Like basically how this formatted is, we have first the ID, then we have salt, and we have hash, right? You can see this is an ID, this is a salt, and this is a hash. Now, this here, for example, if there will be a 1, it means the MD5, or if there was a 2B or 2A, it will be a blowfish. But in this case, this Y here, this is the prefix, indicates the algorithm used for hashing. Now in this case, this Y means is the identifier is for the yes script. Yes, let's actually take notes. Uses yes script algorithm. This is a modern password hashing scheme, successor to script. Now this is designed for stronger memory hard protection, and we also have here is G9T. Now this is the parameters. Now G9T, this is part encodes the hashing parameters, now which controls the cost, which is time memory factors. Now for yes script, this includes values like CPU memory cost, block size, and parallelization. And now the exact decoding will happen on base 64 like encoding specific to yes script, but important part, this defines how hard it is to compute the hash. And basically we have a salt here. This is our salt. Let's actually delete this. Yeah, this is our salt. So let's add this ID or ID or algorithm or ID. This one is parameters, which is cost settings. This is our salt. Now this is salt, basically means this is the salt value randomly generated per password. Now its purpose is to ensure that the same password does not always hash to the same value. So even if two users have the same password, their hashes will differ because of the different hashes. And lastly, we have a hash digest. Now this is the resulting hash, the encoded output of the ESCrypt function. This part changes depending on how the password and salt, both the password and the salt, and it's what password crackers like Hashcat or John the Ripper will attempt to match by repeatedly hashing candidate passwords. In this case, the algorithm is yes script. We can see the hashing cost settings. We are seeing the hash, and we are seeing the hash digest. And that's basically it. Now this ensures even if two users pick the same password, their hashes differ due to different salts. Now that was the output of the etc shadow. Now let's test the cat etc password. Before etc shadow, password hashes were stored in directly in etc passw, which is a word readable, and that posed an obvious risk. Now today this etc passw still exists, but it primarily contains metadata about user accounts. You can see even the Linux doesn't care, which didn't ask for us to run it sudo, or didn't say that the permission was denied, right? So the example output is this. We also have the username, the password placeholder. This indicates this X here indicates the real password hash is stored securely in etc shadow. Now older systems, if you have a lot older kernel Linux, you will probably see hash here. And we have a user ID. This is a numeric ID unique to each user. The 0 here means root. The higher numbers equals regular system users, especially higher than 1000. The group ID we also have here. This is the numeric ID of the user's primary group. So our Tphoenix user has its own group. And we also have the GECOS field. This is a comment field, usually holds full name or account description. In this case, Tphoenix has the same user account. Also, for example, in pools, this field named pools audio daemon. In GDM here, it's named GNOME display manager. And also we have a home directory. You can see here the home Tphoenix, the user's starting directory. Like this is the directory you will start, and it also has lots of other features. Of course, you can see this is the directory we are starting here, and we also have a shell, being bash. This program executed at login. Now normal users use bean bash, but for the service accounts, user spin no login, bean false. For the root account, you are seeing again bean bash. And yes, we have a couple of observations we can learn from here, right? System accounts. System accounts are basically nobody. For example, this one, or like everything here, right? Systemd network, systemd timesync, systemd ohm, or whoopsie, DNS mask. So this exists for services and not for us. They are set to a no login for safety. And your personal account, in this case, my account, Tphoenix, has its own folder on path and bin bash, meaning it is an interactive user. Now if you add a user like with sudo, let's actually clear it, sudo add user test, we need to let's name it, or let's actually add user different, right? We will enter the 123 as a password. Okay, this should be. We will just let's actually close the terminal. Yes, let's add the user. Sudo add user auxiliary academy. Set the password to password 123. P is uppercase here. Oops, this was my password. password 1980, enter the password, or let's actually use another password like or pixel 1234, pixel 1234. The full name is Oxley Academy. The room number is 19B. Work phone is this. Home phone is this. Other just a dummy account. Yes. That's it. And then let's run these following commands. Firstly, etc shadow sudo cat etc shadow, and here we are. You can see the Oxley Academy has its own hash. Again, it uses the same ID algorithm, which is yes script. It has different hash, of course, obviously. And let's test with the etc password, cat etc passw. And here we have all the information here. You see the room number, the home phone or work phone, home phone, account details, the path, and bin bash. This contains metadata, user ID, group ID, and so on and so forth. Now, accessing this etc shadow without authorization is illegal. As ethical professionals, we only perform this in a lab environments during authorized penetration tests, or for system recovery where we are explicitly permitted. And in conclusion, in this lecture, we have explored how Linux handles password storage in etc shadow, how to interpret real-world etc shadow output like hashes, salts, disabled system accounts, how to interpret etc passw output like user ID, group ID, home, shell, placeholders, details like we did in Oxley Academy, and how users, like for example in this case in Typhoonix, are represented with salted hashes and interactive shells. And basically key takeaways of this lecture is etc shadow file stores the actual hashes. The etc passw stores the account metadata. System accounts are restricted with no login or false shells, and salts make each password hash unique even if passwords are reused. And in this lecture in the next lecture we'll move forward from collection into cracking and analysis using John Doe Ripper, and that's where we will put these collected hashes to work. Thank you for watching, and I'm meeting you in the next lecture.